Now the next question is, write the four quantum numbers of the 12th electron of element X whose electronic configuration is 1 is to write the four quantum numbers of 12th electron of an element X whose electronic configuration is 1s2, 2s2, 2p6, 3s2. The question is, write the four quantum number values. Four quantum numbers means first one is principal quantum number, next is angular momentum quantum number, next is a magnetic quantum number, that is ML, and spin quantum number EMS. The question is, write the four quantum number values of 12th electron of an element X whose electronic configuration. Element X was given, it did not mention the name. We can say the name also, we can find the name also. And the configuration given is 1s2, 2s2, and next one is 2p6, 3s2. He is asking, write the four quantum number values for which electron? 12th electron of the given configuration, means 12th electron. He is asking for 12th electron. We are going to find out. Now here if I write, if I count, this is 2 electrons, 4 electrons complete, 10 were completed. In this 11 and 12. So that is 12th electron quantum number values you have to find out. Now I will consider. Please concentrate, which is a very, very important, and sometimes you may feel it is very tricky, but it is a very, very easy question to answer. Okay, if you get this question means you are very lucky to have this kind of questions in the examination. So that is, I am going to write quantum number values for 12th electron. Now if I take 3s2 configuration, in 3s2 2 electrons are there. So very clearly I will mention, this is 3s2 level, 3s2. And this is first electron, this is 11th electron, it will become the 12th electron. So I am going to write the quantum number values for the 12th electron. So that is 12th electron. N value I are going to write, I will write here. So 12th electron, quantum number values, that is N value you are going to write, L value, ML value and MS value for 12th electron. So if I take this one, 3s2. Now in front of, this is s orbital. Okay, and in front of this s orbital, what is the number here there? I will compare this one with NLX, then you will understand more easily. So N value is how much? 3. S orbital, as I mentioned in the previous questions. Okay, L value if it is 0 means S orbital. L value if it is 1 means P orbital. L value if it is 2 means D orbital. Okay, now we have S orbital there. S orbital is there in this configuration. So L value will be how much? That is 0. That is 0. So next we'll be writing what values means ML values. Now magnetic quantum number values depends upon L value. L value is how much? 0. In magnetic quantum number, ML value will become a 0 only. Remember that. Because we have minus L, 0 plus L range of values are there. But ML value will become a 0 here. And MS. Now, according to spin quantum number, 2 spins are possible for a given set of one pair of electrons. One electron will revolve in a clockwise direction, spins in clockwise direction. One spins in anti-clockwise direction. So in s orbital we have only maximum 2 electrons. Now I show this 2 electrons. If the first electron is spinning in clockwise direction, say if it is spinning in clockwise direction, value is plus half. The electron spins in anti-clockwise direction, the value is minus half. Now for MS value, 12th electron is value is spin quantum number value is minus half. So we got the quantum number values. Okay, we have the quantum number values for 12th electron of that is given element. Here, sir, what is element name, sir? Now X is element, your given configuration is 1s2, 2s2, 2p6, 3s2. Now we can guess the element. How many number of electrons? The total 12 electrons are. The element name is magnesium. Element name is magnesium. And quantum number value is 3s1. I told now, that is n is equal to 3, L is equal to 0, ML is equal to 0, MS is equal to minus half, second electron. In the s orbital, second electron anti-clockwise. Okay, that is minus half. These are the quantum number values for last electron of magnesium. Okay, if Hund's rule is not available, guess and write the changes in the electronic configuration of nitrogen. If Hund's rule is not available, guess and write the changes in the electronic configuration of nitrogen. So what is Hund's rule? You should know that. Okay, if Hund's rule is not available, guess and write the changes in the electronic configuration of nitrogen. So what is Hund's rule? You should remember that. Okay. Now Hund's rule or Hund's rule. According to Hund's rule, pairing of electrons takes place. For your information's sake, please note down this. Okay, pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. This is a statement. Or one another way, whenever degenerate orbitals are available, pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron. This is a Hund's rule. So what is the meaning of degenerate orbitals? The orbitals having the same energy. Sir, what is the meaning of degenerate orbitals, sir? Orbitals having a same energy are called as degenerate orbitals. For s orbital, there is no any other type of degenerate orbitals, only one orbital is there in s. Where in case of p orbital, we are having three degenerate orbitals. They are px, py, pz. So all these three orbitals are having same energy, hence they are called degenerate orbitals. So p orbital is having how many degenerate orbitals? 3. S orbital, no other degenerate orbitals, only s orbital we have only one. And for d orbital we are having 5 degenerate orbitals. They are dxy, dyz, dzx, dx square minus y square and dz square. 5 degenerate orbitals are there. So we'll be writing what the question is. Okay, if Hund's rule is not available, guess and write the changes in the electronic configuration of nitrogen. If Hund's rule is not available, what are the changes? Now Hund's rule statement I wrote already on the board. Now if Hund's rule is not available, guess what are the changes we'll observe in the configuration of nitrogen. Nitrogen atomic number is 7. It contains 7 electrons. We know that. If I write the configuration 1s2, 2s2, 2p3, 2p3. Okay. So according to Hund's rule, how to write this configuration? That is mainly first we'll discuss, and after that, if it is not there, now how the configuration will be written in case of nitrogen. How we can write that configuration if Hund's rule is not available. Okay, that is according to Hund's rule. I told pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. I mentioned already degenerate orbitals means orbitals having a same energy are called degenerate orbitals. Now I will write orbital level configuration here. 1s2. For 1s2, now we are having I will write configuration again here. This is 1s2, 2s2, 2p3. So according to Hund's rule, the configuration should be like this. 1s2 means 2 electrons will be filled directly, and here is 2s2, 2 electrons, because s orbital does not have any degenerate orbitals. Now p, we have 3 degenerate orbitals are there. They are 2px, 2py, 2pz are there. So according to Hund's rule, what is the statement? Pairing of electrons. Pairing. Pair means 2, you know. Pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. According to Hund's rule, in p orbital here we have only 3 electrons are there. So how should be the electrons must be filled here? 1 electron. Okay. So 1 electron. 3 electrons are there according to Hund's rule. 1. So here first 1 electron, here 1 electron, here 1 electron. First one should be filled in each degenerate orbitals. 2px should be 1 electron, then it is 2px1, 2py1, 2pz1, 1, 1. Then only pairs. Understood? If this rule, if you write the configuration like this, it will become much stable configuration. Nitrogen is more stable because of half-filled atomic orbital here. P orbital is half-filled. Atomic orbitals with half-filled configurations and a fully filled configuration, those elements or those atoms are more stable. Okay, now here half-filled. 1, 1, 1, 2p3 half-filled and each 1 electron. So this is according to Hund's rule. If Hund's rule is not there, okay, what will be the configuration means? It will become a 1s2, that's right. Okay, and here it is 2s2. Okay, 1s2, 2s2, And here is 2p3 now. If degenerate orbitals are available, pairing of electrons takes place, okay, only when 1 is filled. Now, if you are not thinking about Hund's rule, then how the configuration will be? 1 won't be filled. Here is 1, again 1, and again here. So the filling will be like this. It will become a 2px2. It will become a 2py1, 2pz0 will become. And the element won't be much stable here. Okay, so it won't be a stable configuration. It will be very strong configuration, because if this configuration, the nitrogen can able to participate in bond formation more easily, because in chemical bonding lesson we'll be discussing about it. It will form molecule will form triple bond. So to make the atom more stable, nitrogen atom more stable, we should write the configuration according to the concept of Hund's rule. We should never like this. So if you won't follow the Hund's rule, the element nitrogen becomes much unstable. Reason is not half filled. That is, we are not following degenerate orbitals concept of filling. Just we are writing likely, this means it won't be much stable. Okay, I hope you understood this explanation. Come on, next question. If Hund's rule is not available, guess and write the changes in the electronic configuration of carbon. If Hund's rule is not available, guess and write the changes in the electronic configuration of carbon, even in the changes in the electronic configuration of carbon. See, carbon, atomic number is 6. Okay, and configuration if I write 1s2, 2s2, 2p2. According to Hund's rule, okay, pairing of electrons takes place after all the available degenerate orbitals are occupied by 1 electron each. Now, according to Hund's rule, if I write this, first initially I will write according to Hund's rule. So, Hund's rule or Hund's rule configuration, okay, according to Hund's rule, configuration should be, this is 1s2 and this is 2s2 and this is 2px, 2py, 2pz. So 2 electrons are there in p orbital. Okay. Now, according to Hund's rule, 2 electrons are there now. First one should be filled. And next is 2px1, 2py1. It should be filled. And 2pz0 as usual, because no more electrons. This is according to Hund's rule. If the Hund's rule is not there, we are not applying the Hund's rule. Okay, then how the configuration will be? It will become it is 1s2 and it is 2s2. And here the configuration will become 2px2 directly, 2 electrons will be filled. Okay, and here is 2py0, 2pz0. Is it clear? The configuration will be like this. I hope you understood this. Okay, now the next question is, draw the shape of the orbital whose n is equal to 1, L is equal to 0, ML is equal to 0. Okay, n is equal to 1, L is equal to 0, ML is equal to 0. Which orbital? Now I will explain clearly. This is the nucleus of a given atom. This is the first shell, second shell, third shell. I did not mention which atom is, just simply I am saying K, L, M. Here it is n is equal to 1, n is equal to 2, n is equal to 3. Okay, now according to principal quantum number, n is equal to 1, first shell, K shell, n is equal to 2, second shell, L shell, n is equal to 3, M shell, and so on. According to angular momentum quantum number, L is equal to 0 means which orbital? S orbital. L is equal to 1 means which orbital? P orbital. L is equal to 2 means D orbital, and so on. Okay, now according to magnetic quantum number, ML is equal to, okay, if L is equal to 0, ML value will become a 0. If L is equal to 1, ML values will become negative to positive. That is, I am writing as -1, 0, +1. Is it clear? -1, 0, +1. Now L is equal to 1 means this one. L is equal to 0 means ML value will become ML is equal to -0 + 0. Okay, 0, -0, 0 + 0. We can't take 0 only. Now, here the value is given is n is equal to 1. N is equal to 1 means I can keep 1 here. Okay. Now L is equal to 0 means, I told now which orbital? S orbital. That is 1s. ML is 0. ML is 0. ML is 0 means, that is, which orbital comes means S orbital only. That is, based on this, the configuration, if you wish to write the configuration, I will consider this configuration as, because he did not mention about MS spin quantum number. So I think it might be 1s1. Is it clear? So based on given quantum number values, which orbital comes means S orbital only simply. No need to write even this also. We can write the orbital is 1s simply. That's enough. No need to mention that 1 and everything. This is 1s. Is it clear? Because why I wrote 1s1 means it might be hydrogen, it may be helium also. Because it not give spin quantum number. He has given only n value, l value, ml value means the orbital is 1s. Means s orbital. Clearly, if you want to write, it is 1s. Okay, I hope you understood. Multiple choice questions. Okay, for multiple choice questions, I will solve the answers. First question is, the orbital with the highest energy level among 3s, 3p, 4s and 3d. The orbital with the highest energy level among 3s, 3p, 4s and 3d. And for this, you should have some idea about Moll's diagram. And one more way is n plus L value. Listen. So Moll's diagram, if I draw, this is 1s, this is 2s, 3s, 4s. And even we have, okay, this is enough. Next one is 2p, 3p, 4p. And here it is 3d, 4d. And here L is equal to 0, L is equal to 1, L is equal to 2. Here n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Understood? Now, if I complete this Moll's diagram, first electron into 1s, then 2s, then 2p, 3s, 3p, 4s, and so on. Now, if I write the relative energy levels of these orbitals, 1s is first one, 1s is having less energy, 1s is less than 2s, 2s is less than 2p, 2p is less than 3s, 3s is less than 3p, 3p is less than 4s, 4s is less than 3d. See, 1s is less than 2s, 2s is less than 2p, 2p is less than 3s, 3s is less than 3p, 3p is less than 4s, 4s is less than 3d. Understood? Now order of filling is like this. Now if I complete this, here is 5s, 3d, 4p, 5s. So among all these orbitals, which is having a less energy means 1s. Okay, next is more energy 2s, next 2p, next 3s, next more is 3p, next more is 4s, next more is 3d. Among all these orbitals having highest energy, now here if you see, which was filled last year, after 4s, 3d was filled. So the highest energy is for which orbital? 3d orbital. 3d is having a more energy. Energy of 3d is more than, okay, 4s. 4s is more than 3p. 3p is more than 3s. Understood? So this you can write based on n plus L value, but in the question he did not ask about it. If you want, you can write even that value also. If you wish me to write, then I will write even n plus L value for all these. 3s orbital, n plus L value, 3p, 4s and 3d, n plus L values. Here n is equal to how much? 3. That is 3. Here n is equal to how much? This is a 3p. Okay, n is equal to how much? 3. Here n is equal to how much? 4. 4s. Okay, here n is equal to how much? 3. Plus L value. I told you already. If L is equal to 0, which orbital comes? S orbital. That is L is equal to 0. L is equal to 1 means which orbital is coming? P orbital. L is equal to 0 means which orbital? S orbital. L is equal to 2 means which orbital? D orbital. That is 2 here, right? Then here is 3, here is 4, here is 4, here is 5. Now based on the values also we can write to understand very easily. Among all these, which is having highest n plus L value? 3D. So electron, hence because of that 3D is having more energy. Sir, we have both these orbitals are having same n plus L value we got now. Then why you mentioned that 4s is having more energy means among these two, n value is least for 3p, n value is more for 4, that is 4s. So hence 4s is having more energy, 3p is having a less energy. Okay, so in these two if you take n plus L value is more for which orbital? 3p than 3s, hence 3p is having more energy. Remember that, very important. This kind of questions are. Come on, next bit part. The first question answer is in multiple choice, the orbital with the highest energy level, okay, among 3s, 3p, 4s, 3d is answer is D, that is a 3d orbital. Now the second multiple choice. If n is equal to 4, then the number of orbitals in the subshell is, if n is equal to 4, the number of orbitals in the subshell, n is equal to 4, very easy. Now we should have some basic idea about two particular formulae are there. To find the number of electrons in a given shell, we can use the formula 2n square. Whereas to find the number of orbitals or subshells in a given shell, we can use the formula n square. We can use the formula n square. So here the question is, the bit part question is, if n is equal to 4, then the number of orbitals in the subshell is, if n is equal to 4, then the number of orbitals in the, total number of orbitals, total number of orbitals in the subshell is, that is, we can use the formula n square. N is equal to 4, no, nothing but 4 square. N is equal to 4, if you substitute this, if n is equal to 4, if you substitute in n square formula, 4 square is equal to how much? 16. Then the total number of orbitals, present in the given subshell is 16. Sir, how you got this number, sir? Can you please explain clearly? Means you know that, s orbital, there are no other suborbitals or degenerate orbitals, only one. For p, how many are there? 3. For d, how many are there? 5. For f, there are 7. So together, 1 plus 3 plus 5 plus 7, how many? 16 are there. If you add all these, you will get 16. Hence, like that, you have to find out the number of orbitals in a given subshell is by using the formula n square. That is 4 square 16. Because s is equal to 1. P, how many? 3 degenerate orbitals. If you want, I will write px, py, pz. Here is d, dxy, dyz, dzx, dx square minus dz square. In 7 types are there. So altogether total how many? 16 orbitals are there in a given subshell. N is equal to 4. If you take shell, number of orbitals existing in this is how many? Means 16. Is it clear? Total number of orbitals is 16. Which of the following is the correct electronic configuration? Which of the following is the correct electronic configuration? The next question is, which of the following is the correct electronic configuration? First one given as 1s2, 2s2, 2p7. Second one given as 1s2, 2s3, 2p6. And third one given as 1s2, 2s2, 2p6. And fourth one given as 1s2. Third one given as 1s1, 2s2, 2p6. Fourth one given as 1s2, 2s2, 2p6. So if you check these configurations clearly, 1s2, 2s2, 2p7. In p, maximum number of, x maximum number of electrons 2. P maximum 6, D maximum 10. F, if it is there, means 14. So if you check this configuration, 1s2, 2s2, 2p7. P with 7 electrons never possible. P orbital with 7 electrons never exists. So it is wrong. And here is 1s2, 2s3, 2p6 he mentioned. So 2s3, S maximum is only 2, but he mentioned 3. Hence it is also wrong. And next configuration is 1s1, 2s2, 2p6. Without filling 1s here completely, then how it will go to 2s2 directly? It is never possible here now in this case. So hence this is also wrong. And the fourth one is D is 1s2, 2s2, 2p6. 1s S maximum 2 filled completely. 2s S is maximum 2 completely filled. And P is 6 maximum completely filled. Hence D is the right option. For that particular bit part. Which of the following is the configuration of an inert gas? Which of the following is the configuration of an inert gas? The options given is 1s2, 2s1, 2p7. First one, 1s2, 2s1, 2p7. A option. B mentioned is 1s2, 2s3, 2p5. And next one is C is 1s2, 2s3, 1s1, sorry, 1s1, 2s3, 2p5. And D is 1s2, 2s2, 2p6. So here if you see, what is inert gas configuration? The presence of 8 electrons. What are inert gases? The elements which comes under 8th A group are called inert gases. They are also called noble gases. They are called stable elements or zero group elements. Those elements are helium, neon, argon, krypton, xenon, and xenon, radon, and even oganesson. Okay, so helium, neon, argon, krypton, xenon, radon, and oganesson. So all these are inert gases, and it is having a helium is having a stable configuration, but it is having a duplet configuration. All these are having a octet configuration. Octa means 8. Presence of 8 electrons in the last shell. Nothing but octet configuration. You check once. Last shell, it contains how many electrons? 1s2, 2s1, 2p7. Last shell is this only. But here configuration was given as 2p, 2s1, 2p7. In p orbital, 7 never exists. So it is wrong. And if I talk about B, 1s2, 2s3, 2p5. S maximum 2 only, not more than that. So even though it is having 3 plus 5, 8 is there, but it is not correct. And even 1s1, 2s3, 2p5. Last shell is having how many? 3 plus 5, 8. So by S, more than 2 never exists. He has mentioned 3 years there. So it is wrong configuration, even though it is having a last shell 8 are there. But in this case, D, 1s2, 2s2, 2p6 you got. First shell, okay, satisfied. Second shell, you got 2 plus 6. S maximum 2, perfect. P maximum 6, perfect. So it is having 8 electrons in the last shell. Hence, it is a perfect inert gas. And if you want me to give the name of this one, that is a neon. The element name is neon. Configuration is 1s2, 2s2, 2p6. Perfect inert gas because 8 electrons are present in the last shell. Okay, hence it is having octet configuration. Because of that, it is a inert gas. Come on, next question. The orbital occupied by the 7th electron of sodium atom is, okay, the orbital occupied by the 7th electron sodium atom is, that is 7th electron. He is talking about 7th electron of sodium. Okay, and the options given is 2px, 2py, 2pz, and 2s. But to solve this question, you should have basic idea about the atomic number of sodium first. Sodium atomic number is 11. It contains 11 electrons. And we'll write the configuration initially. 1s2, 2s2, 2p6. As I already mentioned, S does not have any degenerate orbital, 0. Okay. No other types, only one type is there. That is only one type, no degenerate orbital. And P is having a 3 degenerate orbitals. They are Px, Py, Pz. So I will write, I can mention as 2Px, 2Py, 2Pz. Okay. Now I'll write the, if you write the configuration, okay, of sodium 1s2, 2s2, 2p6, this is actually 3s1. Okay, sodium atomic number 11. Okay, sodium atomic number is 11. It contains 11 electrons and the configuration is 1s2, 2s2, 2p6, 3s1. So total number of 11 electrons are there. We should understand the question here. He is asking about 7th electron is occupying which orbital in sodium. That is the question. Now, according to Hunsrud, we should follow here. This is 1s2, 2 electrons filled. And here it is 2s2. 4 electrons is completed. Now, we are thinking about p orbital. P orbital has got 3 generated orbitals. 2px, 2py, 2pz. Okay, here it is. 4 is up to here, 4 completed. Now we need to think about 2p6. Okay, 4 is complete. Remember that. In px, p2px, 2py, 2pz. 5th electron I'm going to write here. 5th electron will fill here. 6th will be here and 7th will be here. Because according to Hund's rule, pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. 1, 1, 1. It will become the fifth electron, it is the sixth electron, it is the seventh electron. Okay. And if you ask eighth electron, it is again filled in 2px. Ninth electron, 2py. 10th electron, 2pz. 11th electron, 3s1. Is it clear? So here is 7th electron is 2pz1. 2px1, 2py, and 2p. This is 7th electron. So 7th electron is in 2pz orbital. Is it clear? I hope everybody understood this explanation. The atomic number of an element is 19. Okay. And 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 is the configuration. Its valency is, okay, the electronic configuration of an element with atomic number 19 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. What is the valency of this element? And he has given the valencies as option A, valency 2 was given, option B, valency 3 was given, option C, 4 was given, option D, 1 was given. Very clearly understandable if you observe this configuration here. 1s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay. Now the valency of this element name is, atomic number is 19, element name is potassium. 19 atomic number. Now, what is the valency of this element? What is the valency from 9th class point of view? If you consider the combining capacity of an element is called the valency, or simple way of understanding the number of electrons present in the outermost shell of a given atom is simply called as a valency. But to become stable, how many electrons it is going to gain or how many electrons it is going to lose, that is also considered as a valency here. So in the last shell of this potassium, which is the last shell here, fourth shell is the last shell. How many electrons are in the last shell? 1 electron is there. To become stable, okay, so you tell me which elements are naturally stable. Elements with 8 electrons in the last shell are more stable. So among all these orbitals, if you consider, which orbital comes under last shell means fourth s orbital, that is 4s1 is the last shell. Here how many electrons are there? Only 1. So to become stable, actually how many should be there in the last shell? 8 electrons should be there. How many are there? Only 1. So to become stable, it is supposed to gain how many more electrons? 7 electrons. Does this s orbital can able to gain 7 electrons like that? It is highly impossible. Okay, last shell if you consider, okay, last shell only 1 electron is there. So to become stable, sir, 8 are required now. So supposed to gain 7 now, which is much difficult. Then potassium will opt one easy way. That is, I will do one thing. To become more stable, I will lose this electron. If potassium loses this electron, if it is losing 1 electron, giving to some other element, which is a non-metal. Okay, then first shell, how many electrons are there? Here 2. Second shell, how many are there? 8. Third shell, how many are there? 8. If it loses 1 electron, last shell of potassium contains how many now? 8 electrons. Then potassium becomes more stable. So as it is losing 1 electron, hence the valency of potassium is how much? 1. Is it clear? Okay. Now, sir, can you give one more example? Okay. Now, as in case of another element, like I will write a configuration of one element, you tell me the valency. Now, 1s2, 2s2, 2p6 is there. Can you tell me the valency of this particular element? First of all, you count how many number of electrons are there. 2 plus 2, 4. 4 plus 6, 10. 10 electrons means atomic number is 10. Here, we can consider like that. Okay. Now, element might be, it is a neon. Element is a neon. So, neon comes under inert gas. Noble gas. Zero group element. So, if you consider this is the first shell. 1s, s orbital, 1s comes under first shell. 2s, 2p comes under second shell. And if you count the number of electrons, 2 plus 6, how many? 8. Is there any chance of gaining or losing of electrons by this particular element? Means no chance. So then hence the valency of this particular element will become a 0, because already 8 electrons are in the last shell. Here second shell is the last shell for this particular element. It neither lose electrons nor gain electrons, nor even share electrons. Hence the valency of this particular element is 0. Is it clear? Okay. The elements with orbitals fully or partially filled are stable. The valency of copper, whose atomic number 29 is, the elements with orbitals fully or partially filled are stable. The valency, the electronic configuration, mention electronic configuration of copper whose atomic number 29 is the question. Please correct this question. I will read out. The elements with the orbitals fully or partially filled are stable. The valency, the electronic configuration of the element whose atomic number 29 is. That is the electronic configuration. Argon 4s1 3d 10. Next one given as argon 4s2 3d 9. 4s2 3d 9. And next one is argon 4s1 3p5 3d5. Next one, argon 3p3 4s1 3d10. So the question was given wrong. The wrong way of asking question. The element with orbitals fully or partially filled are stable. The electronic configuration of the copper whose atomic number 29 is, that is the question of valency. The electronic configuration of the element whose atomic number 29, copper whose atomic number 29 is, that is the question. Now here is argon 4s1 3d10 was given. Argon 4s2 3d9 was given. Argon 4s1 3p5 3d5 was given. Argon 3p3 4s1 3d10 was given. So among all these options, the right option is argon 4s1 3d10. Now argon means 18 plus. Now here is, if you observe this configuration, s orbital is half filled and d orbital is completely filled, because s orbital maximum 2, half is 1. P orbital maximum is 6, half is 3. D orbital maximum 10, half is 5. So orbitals, atomic orbitals with half filled or fully filled configurations are more stable. So hence, 4s2 3d9 is unstable, even though it is a number is perfect only. That is 9 plus 2. Okay, 11 plus 18. How much? 29. Correct only. But configuration is not stable configuration. Here no chance. He has given argon 4s1 3p5 3d5 and argon 3p3 4s1 3d10. No way. These two are no chance. Among these two, the perfect configuration is, I told already, half filled atomic orbitals and fully filled orbitals are more stable. Here it is fully filled, but it is not half, even not full. So less than full and more than half. Here it is half and full. So hence argon 4s1 3d10 is a perfect configuration, stable configuration for the element that is copper. Okay, option A is the right answer. The electron first occupies the following orbital according to above principle. Given is 5s, B is 4p, and C is option 3d, and D is 5p. So the electron first occupies the following orbital according to above principle. What is above principle? According to above principle, electrons always occupies the orbitals having least energy. Okay, above principle states that electrons always occupies the orbitals having a least energy. So among all these, which orbital is having least energy, you should understand. And for that, you can draw Mohr's diagram, or you can go with the n plus L value concept. Mohr's diagram, we know that 1s, 2s, 3s, 4s, 5s. Here is 2p, 3p, 4p, 5p. Here is 3d, 4d, 5d. That's enough. He has given only 5s, 4p, 3d, 5p. Na? So here it is 1s first, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. Okay. Now here first electron enters into the orbital having least energy. First 1s, least energy, order of filling of energy. That is filling up of electrons in the energy increasing or decreasing levels of atomic or energy levels of atomic orbitals. 1s is less than 2s. 2s is less than 2p. 2p is less than 3s. 3s is less than 3p. 3p is less than 4s. 4s is less than 3d. 3d is less than. Next we have is 4p. Okay, and so on. So among all these orbitals, having less energy, 1s. Now here he has mentioned 5s, 4p, 3d, 5p. Among all these orbitals, which is having a less energy, that is 3d. We are having 5s, 4p, 3d, 5p now. So order of among all these orbitals, okay, less energy orbital we have is, which one you consider? That is 3d. After 3d, then only it is going to enter into 4p, then only into 5s, then only into 5p. If I draw here, then only into 5p. Then I will write even. There is 6 and also. Now, if you write here, among all these orbitals having less energy means right option is 3d. Highest energy means which one? 5p. This is high. This is less energy. Remember that. Sir, explain based on n plus L value. I will write even n plus L value for these. N is equal to how much? Here is 5. S is 0. For this one, n is equal to how much? 4. L value is 1 for this. And here, n is equal to how much? N is equal to 3. L is equal to how much? 2. And here, 5p. 5p. N is equal to how much? 5. L is equal to how much? 1. So, n plus L value, 5s n plus L value is 5. Okay. 5 plus 0, 5. And for 4p, n plus L value is 4 plus 1 is equal to how much? 5. For 3d, n plus L value, 3 plus 2 is equal to 5. For 5p, n plus L value is, I will write here, for 5p, n plus L value is, n plus L value, how much you got? 5 plus 1, how much? 6. So, this is having highest n plus L value, hence it is having a more energy. But among all these three, all are having same n plus L value, 5, 5, 5. But the orbital with the least n value, into that the electron first enters. So 3d orbital is having less n value and is equal to 3 here. Compared to this one. Hence, it is having a less energy. 3d orbital is having a less energy. Okay. I hope everybody understood my explanation. Okay, if you have any doubts, you can comment in the comment section. And I hope everybody understood very clearly. Please like, share and subscribe. Thank you.